Hey everyone, welcome back, and today let's solve Leetcode problem 1545 titled Find kth bit in nth binary string. So we're given two positive integers n and k, and the binary string s sub n is formed as follows. S sub 1 is going to be the string of 0, and S sub any index I is going to be S sub I minus 1 plus the string 1 plus the reverse of the inverted of S sub I minus 1 for when I is greater than 1. So the plus is going to denote the concatenation operation, the reverse of x is going to return the reversed string x, and the invert of x is going to invert all the bits in x, basically changing every 0 to a 1 and a 1 to a 0. So for example, the first four strings in the above sequence are going to be as follows, where S sub 1 through S sub 4 are going to be these corresponding respective values. And we need to simply return the kth bit in S sub n, and it's guaranteed that k is valid for the given n. So in example 1, we have the input n to be 3 and k to be 1, and we'd output 0 because S sub 3 is going to be 0, 1, 1, 1, 0, 0, 1, and the first bit is going to be 0, or the string of 0. And so we'd output the string of 0 as our output for this test case. And in example 2, we have the input n to be 4 and the k to be 11, and we'd output 1 because S sub 4 is 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, and the 11th bit of that sequence, or string rather, is going to be the string of 1, and so that be the value we'd output, right? So I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem, and also make sure to look at the constraints and understand what the worst case time complexity could be of this program. And feel free to just think through a solution again for yourself before I show you guys how I would optimally solve this problem. Okay, so honestly, this is a pretty lengthy description. It may get a little bit confusing when you initially read it, and so I'm going to try to summarize it for you guys even more, just to make sure it's as concise and simple as it can really be. So again, we're essentially tasked to find the kth bit in the nth binary string following that specific pattern, and the sequence of these binary strings is going to be defined recursively, where S sub 1 is 0, S sub 2 is 0, 1, 1, S sub 3 is 0, 1, 1, 1, 0, 0, 1, and so on and so forth. And this pattern grows where each string is built recursively using the previous string's data. So to effectively build S at n, we have to take the previous string S sub n minus 1, add a string 1 in the middle, and invert and reverse S sub n minus 1 to actually form that second half. And the challenge here is to efficiently find that kth bit in S sub n without building these huge strings directly, right? And so instead, we're going to use recursion to determine what that kth bit really is. And so step by step, we're going to break this problem down. So basically, we're going to have a base case like we always do for recursive problems, where if n is equal to 1, we want to return the string 0 because S sub 1 is obviously just 0. And for our length calculation, we know that the length of S of n is going to be 2 to the power of n minus 1, and the midpoint is going to be the middle bit, and that's always going to be the string of 1. And so if the kth bit is the midpoint, we want to return the string of 1. So for our recursive splits, if k lies in that first half, we have to recursify on the left half, right? Recurse basically signifies applying recursion on that specific half or interval, right? And if k lies in the second half, we have to recurse on the right half bit, but we also have to invert the bit when we actually return it. So with that out of the way, let's just go ahead and dive straight into the code here. Okay, so I'm just going to directly define my helper function. I'm just going to call it backtrack. Actually, I don't think backtrack is a good name for this. I'm going to call it helper. I don't know, do whatever you want. Obviously, my two parameters are going to be n and k, right? Because those are the two inputs or variables I want to be working with within this helper function, right? Or again, this is going to basically help find the kth bit to recursively solve the problem, and is going to again calculate this kth bit by breaking down the problem into smaller parts until we actually efficiently or optimally solve the problem, right? So we'll have our base case like we always do for backtracking solutions. So if n, in this case, for our base case, if that's equal to 1, we know we have hit our base case, and we can simply return the string of 0, right? And that's because s sub 1 is just the string 0. And this base case ensures that the recursion actually does have a stopping point, and we don't go forever, and we actually have to have a base case to monitor when and what to actually output for each test case, right? And again, this is our base case. In fact, I will just comment it out right here. Base case when n equals 1. I'll have a string of 0. Awesome. Okay, now that I have that, now I want to actually initialize my length, which, like we talked about before, is going to be 1 bit n subtracted by 1. So what this bit really does is it's going to basically bit shift 1 to the left by n positions, where the length of s sub n is going to be 2 to the power of n minus 1. And it's equivalent to basically multiplying 1 by 2 to the n. And so, for example, 1 sub 3 when n is 3 is going to give us 8. Right? And that's because 2 to the power of 3 is going to be 8, and so subtracting 1 would give us 2 to the power of n, which is going to be the length of the nth binary string, which is a very key pattern to actually note to efficiently solve this problem. So once I actually initialize that length variable, I also want to initialize my middle variable, and that's going to be the length, divided by 2, and I'm going to add 1. And note that this double slash here basically signifies integer division in Python, right? So again, we're basically calculating this midpoint of this binary string, again using that integer division. And for any binary string s sub n, the middle bit is always at position length divided by 2 plus 1, right? That is literally the definition of a middle bit. And once I do that, I want to have a series of conditionals like I always do for binary search standard problems. So in the first conditional here, I'm going to say if k is actually equal to the middle value, we can immediately return negative, or rather the string of 1. And like we talked about before, if the kth bit is the middle bit, that means we can directly return the string of 1, and that's because the middle bit of every binary string in this sequence, no matter how large the pattern grows, is always going to be the string of 1. And so we're going to have another conditional, else if, or in Python it's elif, another simplistic feature of the Python interpreted language. And if k is less than the middle value, we know we can recursively return the helper call, passing in n minus 1 and k as our new parameters or variables in that recursion, right? So again, what this is saying is that if k is less than the midpoint, we know that the kth bit is going to lie in the first half of the binary string. And so we have to recur or recursify the left half by calling helper at n minus 1 and k, right? And finally, we'll have an else conditional here, like we always do again for binary search. And in this case, it's going to be basically covering all the cases where k is greater than the midpoint, signifying that it lies in that right half. So in this case, for this else conditional, we're going to return 0, or the string of 0 rather, but that's only if, again, we're going to have to recursively call this helper function, that's only if n minus 1 and the length minus k plus 1 is actually equal to 1. Otherwise, we have to return, or else we have to return the string of 1 for when that doesn't actually happen, right? And again, if k is actually greater than the midpoint, we want to return, or we basically know that the kth bit is going to lie in that right half, and we'll calculate that new position to be length minus k plus 1 and recur on the left half of s sub n minus 1. And since the second half is actually the inverted version of the first half, we have to invert the bit when we actually return it. And so if the bit from the recursion is the string of 1, we have to return the string of 0. And if the bit from the recursion is the string of 0, we have to return the string of 1. Right? And ultimately, outside of this function, we simply want to recursify, or return, rather, not recursify, we have to return helper at n, comma, k. Right? So again, we're basically calling this helper function outside of our definition with the initial value inputs as n and k, and the result of this helper function is going to be returned as the answer to find the kth bit of the nth binary string. Right? That's the value that we're actually returning, either the string of 0 or the string of 1, whatever the kth bit is actually equal to in that nth binary string in this pattern above, right? So unless I made any syntax errors here, they should be accepted and they should be submitted. Okay, let's see what I did wrong here. I probably spelled something wrong here. Let me just make sure I don't have any syntax errors here. If n is equal to 1, return string. Length is equal to 1 divided by... Okay, yeah, sorry. This should be n. I forgot to replace it with a n, and I kept it as 3. And now this should work. And as you can see, this is just about as efficient as you can get. So again, what this overall kind of does is we're basically finding that kth bit in that nth binary string. The key point here is we're doing this without actually constructing the entire string. And we use recursion to determine which half of the string the kth bit actually lies in, and we invert the bit when needed only for the right half. And the base case stops when the recursion, or the base case stops the recursion when n equals 1, and that's going to be the midpoint, and the midpoint check really saves time by returning the string 1 directly for that middle bit. So for the time complexity of this code, this is going to be big O of n, or linear time, because the recursion runs at most n times, reducing this problem size by 1 at each step. And this is much more efficient than just building the entire binary string step by step. And for the space complexity, this is going to be big O of n as well, due to that recursion stack, which can go up to depth of n. So it's going to be linear time for both the space and runtime complexity, right? So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And as you can see, this is just really efficient code. So if you guys enjoyed this video, please subscribe to my channel. And without further ado, I will see you guys in the next video. Bye-bye.